All right, so we are doing kind of the second part of what we started last class today, where last class we did page 14, I believe, where it was just focused on using standard enthalpies of formation to calculate the enthalpy change of a reaction. But today we're going to figure out that we can actually calculate enthalpy change in another way, and that's using this concept of Hess's law. And what Hess's law says is basically it says that it doesn't matter how you get to a chemical reaction. You could take, like you could take the short way, you could take the long way. You're going to end up getting there, and your enthalpy change is going to be the same. And so that's what it means here by it's independent of the route by which the chemical reaction occurs. So I could go straight from, my reactants to my products, or I might have to do, multiple different reactions. But in the end, my enthalpy change is going to be the same. And so this is presented usually one of two ways. One of them may look like this example that we're going to do where they give us two or sometimes three chemical equations like this, and they give us the enthalpy changes for those reactions. And then they tell us to calculate the enthalpy change for this reaction, okay? Now, I don't have enthalpy values of formation for any of these substances, so I can't just look them up on a chart and calculate it like we did last time. But they did give me these reactions up here. And so I kind of like to think of it as it's kind of like a puzzle. I'm trying to make this reaction. So I have to figure out how to put these reactions together up here and make the puzzle, make that final reaction that I want, okay? And I only want those substances. I don't want any extra substances in my reaction. I only want, in this case, I only want C2H6 in the gas form on the reactant side. And then on the product side, I only want 1 mole of C2H4 in the gas form and 1 mole of hydrogen gas. And so, kind of clean this up a little bit. And so what this is going to look like is I have to kind of look at what reaction am I trying to make and look at where the substances are located and how much of them are there. So in this one, I only have one reactant. It's C2H6, and it's in the gas form. So make sure you not only pay attention to the formulas, but also the states, because sometimes you might have things that are like gas or liquid, okay? But it's the same substance. But in this case, it's a gas. And so I want to look up here in these three equations that they gave me up above. Where do I see this substance? I need to locate it. And so if you look, it's here in the first reaction, okay, C2H6 in the gas form. So that's the same exact substance. So it is on the correct side. It's on the reactant side. The only problem is this 2 right here. I don't want 2 moles. I only want 1 mole because in my reaction down here, there is no coefficient, which means it's a 1. So I need to somehow get rid of this 2. And so the only way to do that would be to divide by 2. And so that's what I'm going to do. I'm going to divide this entire equation by 2. And when I say divide the entire equation, I mean that all my coefficients are going to get divided by 2. So I'm going to rewrite it down here. And so if I divide this one by 2, that just makes it a 1. So this would be C. I'm going to do it in black. Let me switch colors. It would be C2H6 because now there's just one of it. And it would be plus. Now, this one, it's a 7. And obviously dividing 7 by 2 is not going to give me a whole number. And so what I'm going to do is I'm just going to leave it in fraction form. I'm just going to leave it as 7/2 oxygens, okay? Because we're not done. We'll eventually finish. So anytime you have an odd number like that, just leave it in fraction form because it's not going to give you a whole number, okay? Then the next one, this one up here, it's got a 4, okay? So that one will change to a 2. And then this one's a 6. So if I divide that one's going to become a 3. So I end up with 2 CO2 plus 3 H2O, okay? So all we did on that was we divided all the coefficients by 2 so that we could have the correct amount of the C2H6 that we need for our final reaction. Now, because I divided all the coefficients by 2, whatever I do to the coefficients, I have to do the same thing to the enthalpy value for that reaction. So this negative 3,120, it also gets divided by 2. So that means now, and I'm going to rewrite it here, that means now my new delta H for this reaction is negative 1,500, and I believe it's 60. Negative 1,560 if you divide by 2 on that one. Let me verify. Yes, negative 1,560. Okay, so that's our first one. So now let's look at what else is down here in this reaction. So that was the only reactant. So now on the product side, I have a C2H4 in the gas form. So let's look for where do I see that up above? Okay, it's not in the, we already used the first equation, so that one's done. But of the two we have left, it's not in the second equation, it's here in the last one. The amount is correct, so I don't need to multiply or divide it by anything. The issue is it's on the wrong side. Okay, it's on the reactant side, and I want it on the product side. So in this one, I'm going to flip my reaction. Okay, I'm going to switch them. And so I'm going to make the reactants products, and I'm going to make the products reactants. Okay, and so if I rewrite it now down here doing that, now my reactants are going to be 2CO2 plus 2H2O. And my products are the C2H4 and the 3 oxygens. Okay. So on that one, we didn't have to multiply or divide. We just flipped it. We switched the reactants and products. If you flip it, okay, what you do then is your sign on your enthalpy flips. So since this was negative 1411, this is now going to be positive 1,411. So if your sign was positive, you would change it to negative. But on ours, since it's starting out negative, we're going to change it to positive. All right, so then the last thing that I have is I have hydrogen gas, H2. So there's only one more equation we haven't used. That's the second one. And if you look, the hydrogen is in it. So seems like we're on the right track. But there's 2 problems. Number one, there are 2 hydrogens. There's a 2 coefficient. I only want 1, so I'm going to have to divide it by 2. But the other problem is it's also on the reactant side, and I want it on the product side. So on the second one, we're going to have to divide by 2 and flip it. Sorry, I clicked on the wrong thing. So I'm going to divide by 2 and flip this one. And so if I divide by 2 and flip it, if I rewrite it down here, okay, I end up with, I have H2O, and there's only one of them because I'm also dividing by 2. And then I have H2 because I divided it by 2. Plus, now in the original equation, there's only one O2 here. And so since I have one O2, but I'm dividing it by 2, I'm just going to do like I did with the 7 in that first equation, and it's just going to be a half O2. Okay, it's 1/2, since that's another odd number. And so by doing that, we reversed it, so the hydrogen is on the right side, and we divided everything by 2, so the hydrogen is the correct amount. And so just like with the other 2, we need to go back and look at our enthalpy change value. And so we have to divide it by 2, and we're going to have to flip the sign. So it's going to become positive 572, and then we're going to divide it by 2. And so it'll actually be positive 200 and, what was it, 572? Positive 286. Okay, so what I need to do now, I need to check, like, have I set these equations up correctly? Okay, so what I want to do is I want to first, like, let's isolate where are the things I want. So here's the C2H6 on the reactant side, and there's only one of it. Here's the C2H4 on the product side, and here is the H2 on the product side. So I have the correct amounts of all the things I want in my final reaction, and they are on the correct side of the equation. Okay, so what should happen if we've done all the math and we've done everything right, everything else should cancel out because I should have the same amounts of everything else on both the reactant and the product side. And so it's like they don't change, they cancel out. So let's check and see how we do. So I'm going to wait and do the oxygens last since they're the ones that have the fractions. Okay, save the fraction ones for last. So I'm going to start with this CO2 right here. So there's 2 CO2. If I look on the other side, here's 2 CO2. It's in this other reaction on the reactant side. So I have one on the reactant side, one on the product side. So they're going to cancel out as long as the amounts are the same. And this is where you also want to make sure your states are the same. On this one, I didn't write the state symbols because they're all the same on this one. But if one of them was like CO2 gas and one was like CO2 liquid, then we could not cancel those out. Okay. So then I have 3 waters, 3 H2O, 3 moles of water. If I look, there's 2 waters here. Okay, so that's part of it, but there's a 3rd water here in the other one. So even if they're in separate areas, I can add them together. So the 2 waters that are here plus the 1 water here, that's a total of 3. And so all of that cancels out with these 3 moles of water that are on the product side. So then the last thing to check is our oxygen. So in the reactant side over here, it's all in one spot. We have 7 halves, 7/2 oxygens. If you look here on the product side, in this reaction, there are 3 oxygens, and in this one, there's a half of an oxygen. So this is where you got to think back to like elementary school fractions and think about how are they equivalent, because 7/2, that's the same thing as 3.5, okay? Because 3 is like 6 divided by 2. So 3 is like 6/2 plus the other half, that's 7/2. And so those amounts are the same. So all those oxygens will cancel out. Okay. And so since everything else canceled out, if I were to kind of rewrite my final equation now, I would end up with this up here. If I rewrite just what I kind of have the pink boxes around, I would end up with C2H6 decomposing and making C2H4 plus H2. So to get the final answer for what's the enthalpy change, once I make sure I verify that everything cancels out and I have everything correct, I just add together these enthalpy values that we rewrote over here. So I have to add them together after I've already done, multiplying or dividing them or reversing the sign. So that's why I like to do it as I go so that I don't forget, oh, I needed to change the sign, or oh, I needed to multiply this by 2 or divide it by 3 or whatever you're having to do. So I would add negative 1,560 plus 1,411, it's positive now, plus 286. And when I add all of those together, I get a positive 100 and I think it's 37. Yes, positive 137. And then my units kilojoules per mole, or kilojoules times mole to the -1. Now, that's the basic process. Okay, so obviously each problem is going to be unique because you're going to have different chemical substances. But the process of looking to find what you need in your final reaction and then manipulating those chemical equations to either, reverse them or multiply or divide them by something in order to kind of make them fit like a puzzle to cancel everything else out and only leave us with what we need, that process is the same. And so you have 3 practice problems that you're going to do. So the first 2, they only give you 2 equations, so they're a little bit easier. The last one, though, it has 3. And so you'll have to kind of do that same process for figuring out how am I going to make the final reaction that I want. And then once you've done all your manipulating, make sure you also do the same thing to your enthalpy values, multiply or divide them by something or reverse the sign. And then once you're done, you add them all up, and that's the enthalpy change for the reaction that you're trying to make. The other way you might see it presented, and you're not really doing an exercise on this one because it's pretty easy to understand, but instead of having those presented to you like that with all the different equations, it could be more visual. So they could show you this, and this is just called an enthalpy cycle because it's kind of circular. So it's kind of like a cyclical. And so this is just a different application of Hess's law. And it says whichever route is taken to get to product C, the enthalpy change is the same. So if I know this enthalpy value right here, that I can go straight from A to C, I don't need to calculate anything. But if I don't know what the delta H number 3 is, but I do know, I know how to get from this substance to this substance, from A to B, and then I know how to get from B to C. If I know these two values, then I can add them together, and that will give me the answer for what is the enthalpy change to go straight from A to C. Okay. And so how you might see it presented is similar to this right here, this example. And again, you're not working it out, it's worked out for you. So essentially, you just need to pay attention to the fact that they have given you, they'll usually give you the enthalpy values. So here they are right here. And so delta H1, this is the negative 105. Delta H2 is negative 2,219. And so since I know that those two, if I put them together, it's going to give me delta H3. So I simply add them, and this would be my value for delta H3 that would go here. The other way you might see these enthalpy cycles presented is instead of asking you to solve for the delta H3, they might ask you for like the delta H1 or 2. And in that case, I would still use this setup of, 1 plus 2 equals 3 for the delta H's. But maybe they asked me to solve for delta H1. Okay. And in that case, I would say, well, delta H1 is delta H3, because that's the total, minus delta H2. So that's really the only different way they might present it, is they might give you that delta H3, that's the total, and they might ask you for one of the other ones, and you would just subtract instead of adding. Okay, but that is essentially it for today, and we're actually going to